Hi everyone, I'm Hendrik Beyer, and this talk is about some work I've done with Michael Keizers at CWI in Amsterdam, titled quite descriptively, Guiding Multiplayer MCTS by Focusing on Yourself. So let's jump right in with the research problem that motivated this. The motivation for this work mainly came from this table published in Pim Nyson's PhD thesis back in 2013. What Pim basically did was a comparison between Monte Carlo tree search on the one side and three different minimax-based search algorithms called MaxN, Paranoid, and BRS on the other side, in a number of multiplayer board games with 3 to 6 players. And what he found was that while MCTS was overall the stronger algorithm, in many of these games, some of the minimax-based techniques could keep up with or even beat MCTS as long as time controls were short, especially at 250 milliseconds per move. I've marked these conditions in red here. Now, this was surprising and unacceptable for me as a believer in MCTS, because short time settings can be quite important. Imagine, for example, playing a real-time game, or a game on weak hardware, or in an environment where you don't have a lot of computing power left over for AI. Or even think of the very short MCTS searches that are used by frameworks like AlphaZero as a policy improvement operator for reinforcement learning. I thought it would be valuable to remove this unusual weakness of MCTS in short multiplayer searches. So in order to fix this, let's first look at why some minimax-based techniques are actually so strong in these cases marked in red. Unfortunately, I don't have enough time in this talk to really explain how these baselines work, but I just want to quickly point out that Paranoid search is sort of the most basic approach among them. BRS and also BRS Plus, which Pim Nyson couldn't know about yet, are improved search techniques based on Paranoid search that do some clever move pruning in addition. And OPPS, which we didn't have complete results for yet in the paper, but which I'm able to include in this presentation now. That's why I labeled this as free bonus content. OPPS is a further improved version of Paranoid search, featuring more flexible and more effective move pruning than BRS+. We've introduced OPPS this year at FDG, and it's now state-of-the-art among minimax-based methods in multiplayer games, so check out that talk as well if you're interested. So what makes Paranoid, BRS Plus, and OPPS strong? First, these algorithms all use the paranoid assumption, the assumption that all opponent players are always conspiring against the root player. This is often wildly incorrect modeling, but it allows for an n-player zero-sum game to be treated as a two-player zero-sum game. Searching a two-player zero-sum game means that alpha-beta pruning can now be applied. And using alpha-beta pruning means that the search can reach the next moves of the root player within a much shorter search time. The root player moves at tree depth 0, and then again at depth n, depth 2n, etc., where n is the number of players. The additional pruning enabled by BRS Plus and later OPPS allows for even deeper searches, reaching the next root player moves even more easily. Now, if you're wondering, what's the deal with these root player moves? Well, what we found is that the root player searching their own future moves can often be a much more important factor for the strength of the resulting policy than considering many of the opponent moves in between or modeling these opponents correctly. We believe this is the deciding factor in many multiplayer domains, the ability to focus mostly on yourself and your, at least short-term plans, without getting too distracted by all the potential opponent moves in between. In many domains, your own plans will be pretty robust to these opponent moves on average. However, an algorithm should be able to detect and adapt when an opponent does have the ability to interfere, as is to be expected in multiplayer games, so simply ignoring opponents completely is generally not sufficient. The main goal of this work now is to apply this insight from the Minimax framework to the MCTS framework in a way that makes use of the specific strengths of MCTS. Our proposed search algorithm consists of two elements that we've discovered to complement each other particularly well: the existing technique of progressive widening and the newly developed technique of opponent move abstraction, or OMA. And in this section, I'm going to explain how these work and how they work together in our approach. So progressive widening, or PW, also called progressive unpruning, is a well-known soft move pruning technique for MCTS. It allows the search tree initially to focus on moves that are heuristically believed to be promising, and over time then gradually increases the branching factor, leaving the asymptotic behavior of MCTS unchanged. Concretely, in each tree node, we order all legal moves with a static move ordering function, and then we determine the number of top-ranked moves that we're going to actually search by the equation on the left here, where n is the number of visits to the current node so far, and c and alpha are parameters determining the rate of widening. In the illustration on the right, you can see how over time more and more children are getting added to the parent node this way. Now, recent efforts in game AI have largely focused on offline generalization, for example by using deep convolutional neural networks to guide searches. Training these estimators offline means that they have to generalize across all states that could ever be visited in any match. And that's why they require very powerful function approximators, and their training is very data and time intensive. An alternative and orthogonal approach to learning in search is online generalization. Here the goal is to make the most out of the limited data we can collect during play, by focusing learning on the states actually relevant to the currently ongoing search. Think of the MCTS tree itself. During play, the tree estimates the value of each move in the precise context of its entire history, from the first move made at the root all the way down to the move in question. These move estimates are unbiased, but they don't generalize or share any information across the tree. When we look at value estimation techniques that do online generalization, however, they can often be described as abstractors. They create a wider learning context by, for example, focusing on only a part of a move's history or a part of the state in which it's made, and generalizing over the rest, abstracting the rest away. The resulting value estimates are then biased, but can be learned much more quickly due to wider contexts appearing more often. And therefore, such abstract value estimates have a lower variance. And learned quickly, they can then be used to guide the tree search, as we'll see in a minute. In this work, we now propose opponent move abstraction, or OMA. This is an online generalization technique that abstracts over opponent moves in every move's history. And I'm now going to describe how exactly these abstractions are computed and how exactly they're used to guide the MCTS tree. So the first question is, how are OMA value estimates computed? OMA keeps value estimates for moves based on a move history that abstracts over, meaning ignores, past opponent moves, and only distinguishes between past moves of the moving player. The toy MCTS tree on this slide, for example, has 3 different occurrences of the same move A, made in different states, 1, 2, and 3. The tree, of course, keeps separate and independent value estimates for the 3 occurrences, because they have different histories, XMO versus XMP versus Y and Q. OMA, however, maps the move A from node 1 and the move A from node 2 to the same abstract value estimate. Because OMA ignores past opponent moves, both of these moves simply have the relevant history X, the only previous move of the moving player. This means that OMA computes its value estimate for this move by averaging over all previous samples of move A in state 1 and in state 2, leading to that quicker learning. But note that move A, when chosen from node 3, for example, has a different OMA history, the move Y, and therefore does not share the same OMA value estimate. So the second question is, how are OMA value estimates used? In every move selection in the search tree, we can now pick actions that maximize a combination of the unbiased tree value estimate and the new biased but lower variance OMA value estimate. There are several ways to combine unbiased estimates with additional estimates from online generalization. A few have been proposed in the literature for the case of RAVE, for example, and we found them to perform quite similarly, so we chose to use the simple formula you can see at the top, a simple linear combination, beta times the OMA value estimate, plus 1 minus beta times the unbiased value estimate, plus the upper confidence bound of UCT. This coefficient beta itself is defined by the equation at the bottom, where E is a parameter regulating the strength of OMA's influence. Because beta always decays over time, we know that OMA's value estimate is going to help kickstart the search, but then gradually phase out over time as the node collects more and more samples and its unbiased estimate gets better. Now, as I said before, our proposed approach to multiplayer MCTS combines opponent move abstraction with progressive widening, which is why we call it somewhat awkwardly MCTS OMA PW here. In this setup, progressive widening has the task of growing a tree deep enough to reach the root player's next moves, and OMA has the task of learning the values of these moves, abstracting over all potentially irrelevant opponent moves in between. In this way, important knowledge about your own future plans can be more easily acquired and more effectively used across the tree by MCTS. Both techniques have parameters that allow to specify exactly how many opponent moves we can initially afford to prune, and also how strongly we can initially rely on the online generalization over opponent moves. In the limit, they converge to no pruning and no generalization, and therefore they do not change the asymptotic behavior of MCTS. MCTS still converges to a Nash equilibrium in our setting here. Our minimax type baseline algorithms don't have this convergence guarantee due to their unrealistic paranoid assumption, as well as due to the hard pruning of moves in BRS Plus and OPPS. So in the next section, I'm going to show our experimental results with progressive widening, OMA, and their combination. All experiments here used 250 milliseconds of thinking time per move. MCTS used no enhancements other than the ones described before, and Minimax used no other enhancements other than iterative deepening, and the same move ordering that progressive widening also uses. We used 6 different test domains for our experiments: Chinese checkers variants with 3, 4, and 6 players, roll-it variants with 3 and 4 players, and focus with 4 players. We're trying to stay close here to the domains, evaluation functions, and move ordering functions used in Pim Nyson's thesis that I mentioned on the motivation slide earlier, so you can find a lot more in-depth information there. For all experiments, I'm going to present only summarized results on the following slides to get our main messages across. In particular, I'm going to show results averaged over all test domains, but you can find the detailed results for each separate domain in our paper. Our experiments are divided into 3 sets. In the first set, we tested the effect of adding opponent move abstraction to vanilla MCTS, as well as the effect of adding it to MCTS that already uses progressive widening. This serves to demonstrate the synergy effect between the 2 techniques. The first bar in this chart shows that using OMA alone leads to a small improvement over vanilla MCTS. Averaged over all test games, it wins 57.3% of games. The second bar, however, shows that when you add OMA to MCTS with progressive widening, it leads to an average win rate of 65% against MCTS with progressive widening alone. And this synergy effect is caused by PW growing the tree deeply enough to reach more follow-up root player moves, which makes it then possible for OMA to generalize their value estimates across the tree. This makes the 2 techniques work together especially well. In our second set of experiments, we then compared MCTS with all combinations of progressive widening and opponent move abstraction against the Minimax-based Paranoid, BRS Plus, and OPPS. This is to demonstrate the improvement achieved over the state-of-the-art for such short multiplayer searches. Remember that our paper only contains results against Paranoid and BRS+. For this presentation, I was now able to include OPPS as a third baseline, so the average numbers you'll see here will be slightly different. That's why I marked this as free bonus content again. The first bar here shows the performance of vanilla MCTS against the baselines. In 11 out of 18 comparisons here, MCTS was the weaker player, with an average win rate across all 6 domains and all 3 baselines of only 36.8%. This confirms what we expected to find from Pim Nyson's work, despite quite a few implementation differences between his versions of MCTS and BRS and ours. The second bar shows the performance of MCTS OMA against the baselines. There was a modest improvement of the average win rate, now 40.8%, but 10 out of 18 comparisons still showed MCTS to be the weaker player. The third bar shows the results of MCTS PW. The average win rates here are raised to 61.1% over all domains and baselines. However, 7 out of 18 comparisons still couldn't show MCTS to be stronger than the Minimax baseline. And the last bar finally supports the main point of this paper again, that progressive widening and opponent move abstraction are ideally used in combination. The win rates against Paranoid BRS+ and OPPS improved only by 4% on average when OMA was added to MCTS without PW. But adding OMA to MCTS with PW increased these win rates by 10.8%. MCTS using both techniques won 72% of all games against the baselines and was significantly stronger than all 3 baselines in all 6 test domains at the 99.99% confidence level. Our third set of experiments, finally, is bonus content as well and wasn't included in the paper at all. Here we measured the average number of tree nodes reached at different search depths by the different combinations of progressive widening and OMA. This is to give some support to our claim that our approach works by reaching higher tree depths. The domain here is 3-player Chinese checkers, and the timing 250 milliseconds per search. All algorithms are shown at optimal parameter settings here, and as you can see, MCTS OMA, the blue line, searches about as deeply as vanilla MCTS, the yellow line. Progressive widening, the red line, allows for much deeper searches, however. And when both elements are combined, even deeper searches are now optimal, as shown with the black line, because those value estimates are at greater depths and then additionally generalized across the tree, making them much more useful. In fact, for MCTS OMA, only 5% of simulations reach the third root player move at depth 6. But for MCTS OMA PW, 56% of simulations reach this depth. This gives OMA much more data to generalize across the tree for the moving player and explains again how progressive widening and OMA work together. And this brings me to the last section of my talk on conclusions and future work. In conclusion, we found MCTS to be somewhat weak in games with more than 2 players, especially at short time settings. We analyzed the strengths of the competing Minimax-based algorithms Paranoid Search, BRS+, and OPPS. And based on this, we developed a combination of the existing soft pruning technique progressive widening and the newly proposed online generalization technique opponent move abstraction. We empirically demonstrated a synergy of these 2 techniques and showed how they significantly outperform 3 different baselines in 6 different test domains when used together at the previously challenging short time controls. The main idea of our approach is focusing your search as much as possible on yourself and only as much as necessary on the opponents. MCTS OMA PW focuses on discovering multi-move plans and abstracts away in between opponent moves as much as possible. We now see several interesting perspectives for future work here. First, Progressive widening, or OMA, are not actually restricted to deterministic, zero-sum, perfect information, turn-taking board games, even though these are very convenient testbeds. In fact, board games tend to have highly condensed environments and strong interactions between players, which might actually be the worst case for this kind of approach. Abstracting over opponent actions should work even better in domains that are, in some sense, more similar to the real world, so that most actions have very localized effects, affecting only a few other agents, and interactions are less common. We therefore see promise in applications such as, for example, multi-robot coordination problems. Second, we expect benefits from integrating the approach presented here with an expert iteration or zero learning framework. On this slide, you can see an overview of AlphaGo Zero's training loop. This could be promising, first, because such frameworks could provide our approach with state-of-the-art, automatically learned state evaluators and move sorters, instead of the hand-coded ones we used in this paper. But also because our approach could potentially provide such frameworks with a powerful policy improvement operator at very short time settings, instead of using vanilla MCTS. And as a final point, in this paper we compared just one specific form of online generalization for MCTS to Minimax type algorithms without online generalization. Of course, both Minimax and MCTS can in principle use many forms of online generalization based on many different types of abstraction, also simultaneously, and there's still much room for improvement. We used a static move ordering scheme for progressive widening, for example. If we used a dynamic one instead, we could actually feed back the knowledge acquired by OMA during search into improving progressive widening for a potential additional boost. The ultimately most interesting and most challenging goal here might be the automatic end-to-end learning of an optimal online generalization technique. And that's the end of my talk. Thank you very much for watching, and goodbye.